All right, so let's talk about ensemble learning and random forests, which I found very interesting. Again, incredibly simple, stupid stuff works pretty well. So first we're going to need a data set. We're going to use these moons again. So we have a curvy data set, and the job is to separate the blue dots from the green dots. And this time the random number generator is seeded properly, so everybody should get exactly the same pseudo-random numbers. All right, so there you have blue dots and green dots, and clearly they can be separated, but there is some overlap, and you need a curved boundary to separate them. So what we're going to do is use an ensemble. We're going to have three different models: logistic regression, scalar support vector machines, and a random forest classifier. Now, we've already talked about support vectors. They just fit a straight line, perhaps in a higher dimensional space, so they can do some curves like polynomial curves. A random forest is like the decision tree we've done, but it uses random boundaries. Instead of bothering to optimize the boundary, it just randomly splits the thing in two and then splits it again. So it can end up splitting it into enough small groups that it separates them, but it doesn't make any attempt to choose the boundary in a smart way. It just randomly chooses, and amazingly enough, that works pretty well. Logistic regression is hard to understand, and I even asked Bard to explain it to me, and still it's kind of hard to understand. They have the workflow. Create a linear equation to model the relationship, then transform the linear regression into a probability between 0 and 1, and then choose a decision threshold. So it's not incredibly clear to me exactly what it is, but it is one of the standard machine learning models. And so we're using these three different models, and this is how ensemble learning works. You train multiple models, and then they vote. First, we're going to use hard voting, where each one of them votes, is it blue or green? And then you just take the majority, like 2 out of 3. 2 out of 3 are blue, 2 out of 3 are green, that sort of thing. That's a simple way to do it. So this will make a voting classifier from those predictors. And you can see here's a logistic regression, a random forest, and scalar support vector machine. Those are the three things. And you make a voting classifier including those three estimators. So again, I'm amazed that it doesn't raise the processing power too high, but this turns out to be a very common technique to improve machine learning model by having multiple models working together. And so here we are, the three machines vote. This one has an accuracy of 86%, the next one is 89%, the next one is 89%, and when you combine them all, you get higher than any of them, because of course that is the point. If they are doing independent judgments, which may be more or less true here, then they're sort of like random measurements of something with noise. So if these are independent operators, then combining more of them should average out the noise. Now, if they're all just triggering on the same cues, then you won't improve it, but apparently they are making sufficiently different decisions here, and that's why you choose different types of machine learning models in the hopes that they will make independent and different estimates of the answer, and the end result will be better. So in this case, it worked. Now we can try using soft voting, because you throw away a lot of information. If the only thing these classifiers put out is their final answer, is it a green dot or a blue dot, then that's not really all the answer. The individual classifier would probably like to say it has a 70% chance of being blue, and you might as well use all that information. So instead of just using hard voting, you can do soft voting here, where it's going to combine the signals coming out and average the percentages, which would use more information from each classifier, and therefore you'd expect to perform better. And so here, this one went up to 91%, and now it gets up to 92%. So it is a little bit better. All right. Well, that's probably within the noise. So now we're going to do bagging. And bagging is where you, in order to, again, to make these independent and different, you don't train them all on the whole data set. You take random samples of the data set and train each classifier on a different random sample. So they will hopefully have different estimates, and now you have more independent predictors. And so this will do it, and amazingly enough, it's going to make a forest of 500 trees. So it's going to have 500 random decision trees, and then combine the output of them all. Which, you know, my first thought is that this would take 500 times as much computing time, but that is not true. Probably because the bagging means each one is using fewer samples. But still, it's amazing how much you can get done with a relatively weak, free virtual machine here, or container coming from Google. It's just, you know, I'm very pleased at how much important stuff we can do with these simple free services. So machine learning has really come of age. I remember when I first heard you could run a large language model on your cell phone, and it's not using an API of the server. It's really running on your phone. These models do not take all that much compute. Now, it takes quite a bit of compute to train them, but once they're trained, running them is just a matter of simple linear calculations, and it doesn't take that long. So anyway, here's what you get with decision trees and with them without bagging. Let me get my explanation of this. Okay, a single decision tree overfits the data. As you can see, it's just got a bunch of if statements, so it's done this ridiculous thing of not even being contiguous. It's going to be red ones here, then green ones there, then red ones there. You can see it's overfitting. It's fitting the particular pattern of these random dots and not the trend that this whole region should be considered green and this whole region should be considered red. But with the bagging of 500 trees, then it averages all that out. So this serves to be a regularization method. So you can see having 500 independent measures average does in fact now follow the trend of the data and not the noise in the data, which is what you want. So it's pretty successful. And there's an accuracy at the bottom. Yeah, 90.4%. All right. So you can do another one where you go down to just 5 trees instead of 500 trees, and it's quite a lot worse, as you might imagine. You don't have enough trees to really get rid of all this bizarre artifactual stuff where you're fitting stuff that clearly doesn't really look like it belongs in the trend. So there's other ways to do it. Then there's AdaBoost. This is adaptive boosting, and here what you do is instead of having multiple independent machines that are each trying to do the whole job, you have the first machine fit the data, and then you have the next machine try to fit the errors in the first one. So this is like a correction term to add to that one. And this is a correction term to add to that one. So this is another way to go, where each one of them is given a different task just to fix whatever the previous one got wrong. So that's another way to go. This is going to do 5 iterations of AdaBoost. So it'll have 5 machines that operate sequentially, one after another, trying to correct the other one's errors. All right, and it shows you the pattern here. So you see it started and eventually converged back, and so here it is with a learning rate of 1, and here's learning rate of 0.5. Just like everything else, remember, a certain learning rate just jerks around without finding the answer. A good learning rate will converge to a good answer here, and it's not too easy to tell the way this is plotted. Oh, here it is, 1, 2, 3, 4, 5. There we go. So this is the one with a too high a learning rate. So as you see, it just jerks around and is unstable and goes back and forth. Here, I think it's here and eventually goes here. You see it nicely zeroes in on a good decision boundary with a better learning rate. All right. And so this one is terrible, 67% accurate. This one is 87% accurate, which is pretty good. All right, and there's another flag defined. And that's all I wanted to show you about that. But here's an example, by the way, with 10 cycles. And with a smaller learning rate, you really do optimize on what looks like a really pretty good fit here. That looks like a realistic measurement of the actual boundary between these two colors. So that's a good one to try.